Okay, so it's a bit of a little review. For single slit interference, when light is shown through a single slit, a vertical slit is what we looked at. The pattern, you get a wide, bright central maximum, and then you get smaller and a little bit dimmer maxima on either side. Y equals 0 is in the center of that central maximum. The equations we derived for destructive interference, so the equations are showing us where the dark spots are located. So the bright spots are constructive interference, which is a really pretty large region. The dark spots are the destructive interference. We came up with a couple equations. A sine theta is equal to m lambda, which you can write as sine theta is equal to m lambda over a. Now, in the single slit interference pattern, theta is very small. That means the sine of theta, the tangent of theta, and theta are all the same thing. So we can write this as theta is m lambda over a, where theta is in radians. From the geometry of the problem, we also know that tangent of theta is y over L. But again, because the angle is very small, the tangent of theta is the same thing as the sine of theta, which is the same thing as theta. So we were able to equate these. So y, the location of a dark spot on your screen, depends upon the wavelength of the light you're using, how far away the screen is. A is how wide the slit is. M is just your multiple. So m equals 1 is the first dark spot, m equals 2 is the second dark spot, m equals 3 is the next dark spot, and so forth. The width of the central max is simply 2 times your first y. When we shine light through a set of 2 slits, we still get that same basic pattern, but inside of it, we get equally spaced bright and dark spots.
So that's kind of like a beat frequency, isn't it?
Sort of, I guess.
And then you get...
In and out of constructive and destructive, yeah. So the thing that's unique to double slits is that they're all equally spaced. So each dark spot is the same distance apart from each other, and they're the same as how far each bright spot is the distance from each other. Again, y equals 0 is smack dab in the middle of the center bright spot. For double slits, we looked at both constructive and destructive equations. For constructive interference, we get d sine theta is equal to m lambda. For destructive, we have d sine theta is a multiple of half a wavelength. And again, the angle is incredibly small, so we can write this as theta is equal to m lambda over d. And this is theta is equal to m plus 1/2 lambda over d. Those are still perfectly valid. This equation over here, tangent of theta is y over L, is also still valid because that's just the geometry of the setup. The tangent of theta is the same as the sine of theta, which is the same as theta. So if we substitute y over L in for theta, we can come up with an equation for y that basically tells us where the points of constructive interference are going to be. By constructive, it's where you see the color, where you see the light. So your book, I believe, puts a C on subscript on there to remind you that it's constructive positions of y. Similarly, if we make y over L in for theta, we get y for the destructive. The difference is the m plus 1/2 term. Now I want to look at what happens as we add more and more lines. Okay, that's a double slit. The slits are a distance of 0.125 meters apart. Sorry, it's just a very... So equal spacing, dark spots are the same distance apart, bright spots are the same distance apart. Now on this particular slide, right now we're looking at the 2 slits, light shining through the 2 slits. I have a set of 3 slits, and then a set of 4 slits, and then a set of 5 slits. So here's the 3. If you can't see it very well, feel free to go closer. But with the 3 slits, we're now getting a white, it looks kind of like Morse code. A line and then a dot, a bright, a line and then a dot, a bright, a line and then a dot, a bright. Okay? So the constructive points of interference are changing as we add more and more lines. If we go to 4 lines, the points of constructive interference are getting more and more defined. They're not as wide as they were before. Here's 5 slits. For me, it's hard to tell what it even looks like back here. It looks like a big blur. Feel free to go up close if you want to look at it. But as we add more and more lines, we're getting more distinct positions of constructive interference. Which brings us to what is called a diffraction grating. Okay, diffraction grating. Let me, for those back home, you can see dot over on one side, on the left. There's actually, oh, I can't see the other one over there. Dots. Someone's head must be in the way of this one. Nope, it's on the cabinet. So, oh, is that way on the door? Oh yeah, I see it now. So, diffraction grating is what we're looking at. A diffraction grating is a whole bunch of lines. Tons and tons of lines, all next to each other. When you have a whole bunch of lines for the light to shine through, the points of constructive interference become very distinct. You just get dots of constructive interference. This particular diffraction grating it tells me there are 610 lines per millimeter. So in a millimeter of space, there's 610 lines in there. So they're incredibly close, and there's a whole bunch of them. So the fact that they're so close is why the diffraction gets so large. That first point of constructive interference is way over there on the wall. So the diffraction is very big, and because there's so many lines, the constructive interference is very distinctly in one spot. We can figure out D from this. D is not 610. D, the distance between the slits, 1 over 610 millimeters. So the distance from one slit to the next is incredibly small. Okay. Now it turns out, since it's just the constructive interference that's so distinct, we simply look at the equations for constructive interference. Just like double slit, d sine theta is the extra distance one wave travels compared to the other. As long as that is a multiple of a whole wavelength, you get constructive interference. So d sine theta is still equal to m lambda. That's still perfectly valid. Tangent of theta is still y over L because we have the same general geometry of the problem. So go back to your picture from yesterday. Biggest thing. The angles are not small. If you draw a line from that diffraction grating to this dot, and a line from that diffraction grating to that other dot, there's a big angle between the two of them. So what is that going to mean for our equations if theta is not small? We can't say sine of theta is the same as tangent of theta. We cannot substitute y over L in for sine of theta. That won't work. You have to keep tangent and sine in the equations. So if you know y and L, inverse tangent, find theta, come back here, take the sine, so forth. So we just can't make the substitutions that the sine of theta and tangent of theta are the same. So sine of theta does not equal the tangent of theta, which is fine. That doesn't really make that big of a deal. We can do inverse sine and inverse tangent just fine on our calculators. So I have another diffraction grating here. This one's even finer than the one I was shining the laser through. I'm going to shine the light from the overhead projector through this diffraction grating. Whoops, let me turn it on. And we get a nice rainbow. Notice the violet end is not diffracting as much as the red end is. The wavelength. The wavelength of violet light is smaller than the wavelength of red light. So if you go over to our equations over there, for a smaller wavelength, lambda, we're going to get a smaller angle theta. Smaller angle theta means we're going to get a smaller y value. Y is still measured from the absolute center of whatever center on the screen. Okay, so y is the middle of this rectangle right here. I'm trying to think of what color to call it, but I'll give up. So, yeah, peachish color, that works. So, the rainbow, we get one on either side, we would call that the first order rainbow, because it's the first maxima on either side. Now it's kind of hard to see, but there is a second order rainbow. It's a lot dimmer off to the side of the bright one. So the first order one here is the brightest, and it's easiest to see. The second order is still in there though.
I think you can see a little bit better on that left side.
Yeah, you can. And notice the violet of the second order starts to overlap with the red of the first order. So m equals 2 is the second order. M equals 2 with the violet wavelength starts to interfere with m equals 1 with the red wavelength. Okay? So diffraction gratings are very commonly used to spread light into its individual wavelengths. Because D is so incredibly tiny, that makes the diffraction quite large. If D is really, really tiny, all the wavelengths are going to have their own unique angle that they show up at. So we get we can get what's called a spectrum. So this is what we were seeing with this particular diffraction grating. White light, regular light bulbs emit all wavelengths. And that's why we could see a whole rainbow. Neon lights, fluorescent lights, they have a certain type of gas inside of them. And what happens is the electrical current causes the electrons in that gas to jump up to higher energy states, but they don't particularly like to stay there. They jump back down. The energy they absorb to jump up is how much energy they release as they jump back down. And they release it in the form of light. Okay? So each different type of element has certain wavelengths that it will emit because there's only certain energy levels in each of their atoms. Each atom is unique. Each atom has certain energy levels that exist, energy levels where the electrons can jump to. And so each element will emit a very specific characteristic set of wavelengths. Chemists can use this to figure out what things are made of, but astronomers also use it in order to determine what stars are made of, for example. So, and they also use it for the Doppler effect. For example, here's what the spectrum of the sun looks like. These black lines are the energies that are absorbed by the gas in the outer layer of the sun. They're drawing this line up to show you that they match up with hydrogen. They also match up with some of the helium. If a star is moving towards or away from us, these lines that we expect to be there will be shifted. If those lines are shifted towards the red end, it's the redshift, the Doppler effect. Redshift is moving away, so they can figure out how fast it's moving away from us. And if it's moving towards us, then the light will be shifted towards the blue end, a blue shift. Okay. So diffraction gratings allow us to take light and spread it into its constituent wavelengths.